Greetings once again, students. Today we are taking a look at how geoscientists study and identify sedimentary rocks. So let's get started. Sedimentary rocks are important for so many reasons. I love historical geology, which is the major branch of geology concerned with the evolution of the Earth and its life forms from its origin to present day. Sedimentary rocks harbor a lot of history. The size, shape, and accumulation of the sediments help us understand ancient environments. That means that we can look at these sedimentary rocks to help us interpret the past. How do sedimentary rocks fall into the rock cycle, you ask? Well, other rocks are weathered to create the material, sediment or ions, that comes together to form a sedimentary rock. I call this process wedackle, which stands for weathering, erosion, deposition, accumulation, compaction/cementation, and lithification. Weathering and erosion we covered. Remember that during the process of weathering, rocks can be broken into pieces and ions. Deposition refers to the laying down of the pieces of rock, but it can also refer to the crystallization of the ions to form a solid out of the solution. Those sediments, also known as clasts, accumulate over time in various environments. Then the process of lithification occurs. How? The material is compacted and the water is squeezed out and evaporates. As this happens, ions bond together to form crystals, aka minerals. These minerals crystallize on their own to form a full-on chemical sedimentary rock, or the minerals crystallize between the clasts to glue the particles together. Because of my interest in historical geology, I also have an affinity for fossils, which are the remains of once living organisms that are older than 10,000 years. Think about it. Organisms can't be buried in lava, they'll fry. So they have to be buried and preserved in material that is laid on top of them. You can actually preserve the body of the organism or the trackway it makes. Fossils are useful in helping us interpret ancient environments, but they can also help us tell time. Certain organisms only live during specific time periods. If I find a velociraptor, I know that I'm looking at Mesozoic age rocks. Fossils are the timekeepers of sedimentary rocks. Thank you, fossils. As I alluded to before, there are those sedimentary rocks that are composed of pieces of other rocks, and those are called clastic sedimentary rocks. There are also chemical sedimentary rocks that form when minerals precipitate from ions that have been dissolved in an aqueous solution. And then there are my favorite, which are bioclastic sedimentary rocks, which are made from the accumulation and compaction, cementation of organisms. We're going to see all of these today. Let's start with clastic sedimentary rocks. They are composed of pieces. Remember last lab, when we looked at the energy required to transport the clast increases with increased size of the clast? That's what this chart illustrates. I'm sure you can imagine that it takes less energy to move a clay-sized particle than a pebble, cobble, or boulder. I mean, look at the size of that clay-sized particle. It's less than 1/256th of a millimeter. Wow, that's small. This table will be very useful today. You see the particle size, the distinctive features, the depositional environment, and the name of the rock that comes from the wedackle process. As a reminder, wedackle is something I made up and will not be found in your textbook or lab manual. Let's go through examples of each of these rocks. This is a breccia. We say that this sedimentary rock has a coarse grain texture because the grains are greater than 2 millimeter in diameter. Notice that the breccia has angular grains in a finer grain matrix. These types of rocks often hearken to a high energy environment, such as the deposition of sediment from a mass wasting event. The photo on the right shows one of our geology classes in front of a giant breccia. Do you see those big clasts? Here is a hand sample of a conglomerate. Do you see how the clasts are rounded? That is different from breccia, right? Rounded clasts tell a different story. These clasts have moved farther from their source and the edges are worn. You'll find these types of sediments in rivers and by oceans. And since the present is the key to the past, if we find conglomerates, we have an idea of this ancient depositional environment. Both a breccia and a conglomerate are considered poorly sorted because they have different size grains in one rock. Now let's look at rocks composed of sand-sized grains. These sand-sized grains are 1/16 to 2 millimeters in diameter. This is Arcosic sandstone. It is composed of angular feldspar grains mixed with coarse sand. These grains are fairly well sorted. The color is usually pink, reddish-brown, or buff, and the depositional environment is near rivers in sandbars. Quartz sandstone is composed mainly of sand-sized quartz grains. They are usually rounded and well sorted. These are indicative of a beach and/or sand dune deposit. Here's a great photo showing the difference between the two. Notice how the textures are slightly different? We use those differences to help us again understand the environment of deposition, which in turn helps us understand the history of the location. Here is Greywacke. It's a poorly sorted sandstone with angular to subangular clasts. These are often indicative of an ancient underwater landslide known as a turbidity current. Silt is a clast that is bigger than clay but smaller than sand. Silt lithifies to form siltstone. Silts are indicative of floodplains and the outer parts of deltas. Shale is another clastic sedimentary rock. It is composed of clay-sized clasts. Shale is indicative of a low-energy environment of deposition, like the deep sea or a deep lake. You often see layers in it. Shale is one of the most abundant sedimentary rocks on the planet because it covers so much of our sea floor. The oceans make up about 70% of the surface of the Earth. That's going to be a lot of shale. Take a look at these three rocks. Sometimes they get mixed up with each other. Just remember that Greywacke has sand-sized particles, siltstone has silt-sized particles, and shale is composed of clay-sized particles. Shale often shows layering. Another group of rocks you will look at today are the chemical/biogenic sedimentary rocks. Notice how the minerals in these rocks are ones that you've seen before: calcite, dolomite, halite, gypsum, and quartz. Biogenic sedimentary rocks, by the way, are those rocks that originate from a biological source. The hardnesses of the minerals help us identify the chemical/biogenic sedimentary rock. Calcite and dolomite are common minerals found in chemical/biogenic sedimentary rocks. As you know, calcite fizzes when you put acid on it, but dolomite, the cousin of calcite because it has some magnesium thrown in with the calcium in the crystal structure, only fizzes in powdered form. Calcite is found in limestone and dolomite is found in dolostone. Here is an example of limestone. It is fine-grained with interlocking crystals. Limestone is indicative of shallow marine environment. Imagine the Caribbean or the Coral Sea. Fossiliferous limestone is sometimes called a bioclastic rock because it is composed of pieces of biological material. These shells were buried together and cemented with calcite. Fossiliferous limestone doesn't just have to have shells. It can be composed of the exoskeletons of any organism that is cemented within a calcite cement. The ancient depositional environment? You guessed it, the same place that these types of organisms would live today, shallow areas of the oceans. Here is coquina. Most of it is composed of small shell fossils, more than 90% of it in fact. It is held together usually with a calcite cement. Will it fizz when you put acid on it? For sure! Here's another calcite-rich rock, oolitic limestone. Notice the tiny spherical grains called ooids. They are indicative of a shallow marine environment, like the inlets to lagoons. Chalk is composed of the microscopic calcareous-rich exoskeletons of planktonic organisms. The microorganisms die. Their exoskeletons sink to the seafloor and create layers of chalk. Here are the White Cliffs of Dover in Great Britain. Yep, all chalk. Dolostone looks a little like limestone, but it is usually a little darker. Also, it has dolomite instead of calcite, so the rock will only fizz in powdered form. Dolostone has a great texture to it. It's called elephant skin texture. The real elephant skin is in the top right photo. Dolostone is on the bottom right. Depositional environment, shallow ocean. Now we jump into those minerals we were talking about earlier, gypsum, quartz, and halite. You investigated their mineral qualities in a past lab. Now let's look at them in rock form. Rock gypsum is gypsum. It's just layers and layers of it. And where does it come from? It crystallizes in areas where water is evaporating, and there is an abundance of calcium and sulfur. Where are sites of high evaporation? Ephemeral lakes in the desert and even near ocean margins in hot climates. Rock salt is composed of the mineral halite. This is another chemical sedimentary rock that belongs in the evaporite group and forms in the same types of environments. In this case, the water must have an abundance of sodium and chlorine. Shallow marine environments and shallow saline lakes have these constituents. Rock salt forms the same way today as it did in the past. Chert is a chemical sedimentary rock composed of microcrystalline quartz. Do you see its hardness and conchoidal fracture? It's a dead giveaway. Chert forms as silica crystallizes and precipitates out of a silica-rich solution. It is indicative of a deep marine environment. Finally, we come to coal. It is composed of organic material. Coal is the accumulated remains of squished plants that originally lived in swamps and bogs. When you hold a piece of coal in your hand, the first thing you notice is that it feels really light. Why? No minerals. So there you have it, another life-changing experience in your geology lab. Sedimentary rocks help us understand the history of the Earth. Gaia's story, the Greek goddess of the Earth, is revealed as we learn her language. Have you decided to give the geosciences a try yet? It's a viable career. Join us. I want to thank my colleague, Katie Van Sydow, for creating 99.9% of the content for these slides, and my son, Jake Kingsbury, for providing the music. Take care and make it a great day. I'll see you for the next lab.